Well, let's look now at some more examples. There's quite a few of these examples. We'll go through a bunch. There's probably some more in the text. And you may want to just do one or two at first, work them out, and then listen and do some more. Because the learning really comes from the doing. So, the first example is, as we've been saying, it's very important to avoid page faults. They cost a lot of money, a lot of time to do that. And one way to do that is you want to avoid having discontinuous memory. What does that mean? And the words here are almost always worse than the concept. Here, for example, is a little snippet from a Fortran program. And you can think of it Java, C, it'll be the same. Here in Fortran, we just have a bunch of variables we've put in common. So that's just an area of memory that will get reserved. This could also be just a statement of double. You're declaring these variables to be double precision, floating point numbers, and this is the different sizes of them. Okay? So this is the declaration of the program, right up here, variables, and then that we have some do loop which uses elements, what? Z and part J and YLT and med. Okay? So what you see here is we have Z, YLT, part, and med2 used in the calculation, and in between them is this hog, this memory hog, Z part, that takes up a lot of room. Here it's, I don't know, 100,000 memory locations, okay? And that's bad. That means when our statement down here in the do loop tries to get to med2, med2 is over here has to be in a very different part of memory than a part is, or YLT is, or Z is, and so there'll be page faults. You can't avoid it. Okay? So one way of improving your chances of this not happening is to be careful the way you put the variables in memory, the order in which you declare them. So the obvious solution here is to say, move this big memory hog over, out of the way, and it's associated with variables that get used with it. These don't get used together. So you have variables that are used together, kept together, even here in memory, by doing it in the declaration statement. Not very hard, but it makes a difference. It can make a world of a difference. Okay. Now, that's page faults we were talking about. Now let's look at slide 10. Slide 10, we get even a little more subtle. We say, how do you program for cache? How do you make sure, even if the memory, or even if all the variables are in RAM someplace, how do I make sure I can handle them as quickly as possible? Well, this is particularly important for high performance computing, because what you have is a very fast, or fast RAM, you have very fast cache lines, and ultra fast CPU. And what you want to do is never have the ultra fast CPU waiting around for something to be loaded from fast memory, because that means it's ultra slow, it's an ultra long wait, and that speeds up the problems. Often it speeds up the problem by a factor of 10. Again, so these are just not, if this is 10-20% effect, I wouldn't worry about it. But if it's a factor of 10, even 2 or 3, and this could be a factor of 10, then this could be important. It's not true for all problems, but again, when you have very large matrices, it becomes a serious problem. So one uses the term in computing, high-performance computing, stride, and that's the number of array elements that have to get stepped through to perform an operation. So if you have some calculation you want to do, you can say, how far apart in memory are the elements used in the computation? It's in one step, let's say, and if they're very far apart, you'd say, oh, I have to make a big stride to get from here to there, and that's an issue. So one example would be in equation 1 here, the trace of a matrix, defined to be the sum of diagonal elements. Well, that's always, the diagonal elements, they're always a distance of the length of a row or column apart. That has very bad stride. Excuse me. And that's a very hard item to compute well unless you rearrange the elements ahead of time so they're nearer to each other. If you do a simple addition, such as adding x sub I and x to the I plus 1, that's very good stride. They're right next to each other. Mathematically, they should be right next to each other in memory. So the rule is always try to keep the stride low, preferably 1. In Fortran, excuse me again, how do you do this? Well, in Fortran, and here's the rule of thumb, 2 rules of thumb. In Fortran, since the elements in the matrix are stored in memory in column major order, this way, this way, this way, then you want to have the left-hand index of an array vary first. That gives you the most rapid variation of that index, and then you'll be closest to the elements. In Java and C, where the elements are stored across as rows, then you want the right-hand array index, which is the column number, to vary the fastest. Okay, so you have that as the first index in a loop. So let's see that in example. Okay? So we're trying to have here on slide 11 an example of what happens when you have cache misses and you have cache non-misses when you hit it, when you have all the variables in there or not in there as needed. And what's good here is we can't but fail have something that works for one compiler and fails for the other, and vice versa. So again, Fortran stores the array elements in row column major order. Java stores them in row major order across. So just do a simple operation here. Load up a matrix column by column and compare the time it takes to load up the same matrix row by row. If the world was fair, it should be exactly the same time. Same number of elements, it's just changing the order in which they're accessed. And so here we have 2 different versions of doing it. To add up an element, build up a matrix column by column, we have the first do loop here, in which we're varying j, which is the rightmost element. Okay, so that's sequential column reference. The second do loop, we're varying j, which is the row. So it just loads up the matrix in different order. If these 2 do loops take a different amount of time, then you know cache misses is important. Okay, one version will always be good, one version will always be bad. So this is an example of, even though page faults is important, and how items are retrieved from RAM into cache and into the central processing memories, that's not the full story. Okay, these cache misses, which deal with the actual cache going into the central processing unit, can be important as well. So you try them out. Okay. So now here on slide 12, take a look at them. 2 examples for you to run on your own. Take home, practice these. And if you can, run it both on Fortran or C and on Fortran and C, or Fortran and Java, because one will be good for one case and bad for the other. Okay. So in the first index, the first little snippet here we have of code, we have the loop. It's a double do loop with a vector, I dimension, j dimension, fine, and we're going over the full dimension, and all we're doing is doing a product, vector ij times vector ij. So it's just a multiplication, and we do that all the time. And here we have index I, which is the first index, which is the row index, varying most rapidly. So if the row index varies most rapidly, that means you're going down the columns. So I'll say that again. If we vary the row index rapidly, that means we're going down the columns in the matrix, and that's how Fortran stores it. So this is good for Fortran. This will be fast in Fortran. But if you do it the other way, which is varying the column most rapidly, so it's exactly the same equation here, we've just interchanged the 2 do loop orders, then we vary the column most rapidly. This should be bad in Fortran. So if you have a Fortran compiler, compare these 2. See what the difference is. If there's a significant difference, then you know that cache flow does matter. Likewise, if you have a C compiler, or just Java, either work, compare Java or C, again, with the code written in these 2 different ways. What was good for Fortran will be bad for C. What was bad for Fortran will be good for Java. And if it's a significant difference, then you know cache matters. So, let's look at another example. This is a hard example, but I think you're getting the idea. This is matrix multiplication. And what's hard about matrix multiplication is, you know the rule. We have matrix C, which is equal to the product of matrix A times B. And the rule says you go across row by row in A, and you match that up column by column to B. So you multiply element by element in one row of A times element by element in the column of C, which is just the definition here. So why this is a bad example is, well, what's good for one A will be bad for B regardless of the language. Okay? So that's right. So it's a compromise because you are using both columns and rows. So in Fortran here, we again try to minimize the stride by having, we have do loop I, J, and here's do loop K. And here's the multiplication K. So we have I on the outside varying the least rapidly, J in the middle varying more rapidly, K varying the most. We put it together that way. So that's good for Fortran. But we now reverse the order here, J, I, and then the other index, K. We reverse the loop order, so we still have the K's there. This is the same, but the loop order of K and J have now been reversed. Okay? And this should be much better for Fortran, whereas for C. So try these out, and then remember what you have to do to get to speed. And in any case you write a program dealing with large matrices, you can always try different orders of the loop if you can't remember exactly what you should be doing to see which gives the best performance. Okay, so you can do this experimentally. So that's what you should be doing. Go to your lab and try these out experimentally. What do you take home with you? Well, you take home with you, number one, some feel of whether it matters, and number two, the thought that if it does matter, you can always experiment with these orders of loops to get the best performance. It gives you the same mathematics, but it can give you much faster results. So, go ahead and try it, and now we'll get on after this to go back to some doing pure science. But this is how you look inside your computer, and hope you've enjoyed the view. Bye-bye.